Today we're going to do 2.8 subspaces of R to the power of n. A subspace of Rn is any set H in Rn that has three properties. The zero vector is in H. For each u in V in H, the sum of u plus V is in H. And for each u in H and each scalar C, the vector Cu is in H. Let's look at example 1. If vectors v1 and v2 are in Rn and H equals the span of v1, v2, then H is a subspace of Rn. To verify this statement, note that the zero vector is in H. So the span of v1, v2 is a plane through the origin. So we have two arbitrary vectors in H. So our two arbitrary vectors in H are u1, which equals, this is just an arbitrary vector, so it equals S1 V1 plus S2 V2. And we have V1, which equals T1 V1 plus T2 V2. Then U plus V equals S1 V1 plus S2 V2 plus T1 V1 plus T2 V2. Then looking at this, V1 is common in the first and second term, so we could factor that out and have that times S1 plus T1. Just like V2 is common in the second and fourth term, so we could factor that out and have S2 plus T2. Therefore, U plus V is a linear combination of V1 and V2 and hence is in H. Let's look at column space. The column space of a matrix A is the set column A of all linear combinations of the columns of A. If A is A1 to AN with columns of Rn, then column A is the same as the span of A1 to AN. Let's look at example 2. Let A be that matrix and B be the other matrix. Determine whether B is in the column space of A. So B is a linear combination of the columns of A if and only if B can be written as AX for some X. That is, if and only if the equation AX equals B has a solution. So we're going to see if AX plus B has a solution. Or AX equals B has a solution. So we would write our augmented matrix. So the first thing I'm going to do is I'm going to take 4 times row 1, add it to row 2, and negative 3 times row 1 and add it to row 3 to eliminate, to get zeros in my column 1. So row 1 is going to stay the same. Row 2 would become 0, negative 6, negative 18, 15. Row 3 would become 0, negative 2, negative 6, 5. The next thing I'm going to do is take row 3 plus negative 1/3 row 2, or row 3 minus 1/3 row 2 to eliminate, and if you notice that, that's going to eliminate the entire row 3. So looking at this, we know that AX equals B is consistent, and B is in column A. The null space. The null space of matrix A is the set of all solutions of the homogeneous equation AX equals B. Theorem 12. The null space of an m by n matrix A is a subspace of R to the n. Equivalently, the set of all solutions of a system AX equals 0 of m homogeneous linear equations in n unknowns is a subspace of Rn. Basis for a subspace. A basis for a subspace H of Rn is a linearly independent set in H that spans H. Let's look at example 4. So we need to find the basis for the column space of matrix A. So what that means is we first need to obtain the reduced and augmented echelon form for AX equals 0. So I'm going to go ahead and write my augmented matrix. And through different row operations and interchanging rows, I first can end up with a matrix that looks like this, where I have zeroed out the bottom row. Okay, but I still need to obtain, for this pivot column, a 0 above the 4. And to do that, you're going to end up with some decimals, which is fine. So I ended up with 100, negative 300, 010, 1.5, 1.25, 0, and all zeros in my last column. So this corresponds to x1 minus 3x2 plus 1.5 x4 equals 0. And x3 plus 1.25 x4 equals 0. So now we need to solve for the basic variables and write the solution of AX equals 0 in parametric vector form. So I would have x1, x2, x3, x4 equals 3x2 minus 1.5 x4. x2 is just x2. And then I would have negative 1.25 x4 is what x3 equals, and then x4 is also free. So then, writing this in terms of my free variables, I'd have x2 equals 3, 1, 0, 0, plus x4 equals 1.5, 0, negative 1.25, 1. So the basis for null A would be those two vector columns. So my basis would be 3, 1, 0, 0, and negative 1.5, 0, negative 1.25, 1. And let's look at example. It says 3 here, but this should really be example 4. Find the basis for the column space of matrix A. So let's look back at the previous example. Obtain the reduced echelon form. So when I did that with A, this here, negative 3, 2, 3, 9, negative 6, negative 9, 2, 4, negative 2, negative 7, because that should be a negative 7, even though there isn't one here. 8, 2. Reduced down to 1, 0, 0, negative 3, 0, 0, 6, 4, 0, 9, 5, 0. And if I look at this, my pivot columns are here. So the basis for column A uses columns 1 and 3 of A. So the basis of column A would be negative 3, 2, 3, 2, 4, 2, where I have those pivot columns.